Have you ever stopped to think about how companies ship something massive, like an engine block, without the packaging itself weighing a ton? Well, today we're pulling back the curtain on a really powerful but kind of misunderstood manufacturing process that makes it all possible. We're talking about structural foam injection molding. Let's dive in.
Right off the bat, here's the classic engineering puzzle. How do you make something that's got to be huge, has to be tough enough to take a beating for years, but it also needs to be light enough for a person or a robot to just pick up and move? That's the big challenge we're going to solve today.
So let's get really specific with a problem that I know keeps packaging designers up at night. The industry term for the custom stuff that holds and protects parts during shipping, that's called dunnage. Now imagine your job is to design a huge piece of this dunnage that's going to be used over and over and over again. And the list of demands is just brutal. It's got to be enormous. We're talking the size of a card table. It has to protect these super valuable, critical surfaces on every single trip, no exceptions. It needs to survive like years of being banged around in factories and on trucks. And after all that, it's got to be lightweight. These things are constantly pulling in opposite directions.
So what do you usually do? Well, you could use standard injection molding. It makes really strong parts, for sure. But for something this big, the massive force you need to hold the mold closed, that's called clamp force, means the machines get crazy expensive fast. On the other hand, you've got thermoforming. It's awesome for making big shapes quickly, but it's kind of like stretching out pizza dough. It's really hard to keep the thickness consistent, especially when you need thick, beefy ribs for strength. So you see, there's a gap.
And that gap, that's exactly where structural foam comes in. It's this really clever process that fits perfectly between those two other options. And honestly, the best way to get it is what I like to call the waffle cone secret.
Seriously, just picture it. A solid ice cream cone is strong, yeah, but it's also pretty dense and heavy, right? But a waffle cone? It's just as strong, but it's way, way lighter because of all those little air pockets inside. Structural foam is literally that exact same idea, but for plastic parts.
So, now that you've got the waffle cone in your head, here's the official definition. Structural foam injection molding is a process that makes parts with a solid, tough outer skin, like the outside of the cone, and a foamed, cellular, lightweight core on the inside. You get the best of both worlds.
So how does this actually happen? It's a pretty elegant three-step dance. First, you inject plastic that's been mixed with a special foaming agent into the mold. Step 2, as soon as that hot plastic hits the cooler walls of the mold, a solid skin forms instantly, creating that tough outer shell. Then, and this is the really cool part, that foaming agent inside kicks in, creating a lightweight cellular core that expands and pushes outward, filling the mold perfectly. It's almost like you're baking a loaf of bread that has a perfect crust built right in.
Okay, so we have this amazing waffle cone structure. How does that actually solve our designer's dilemma from the beginning? Let's break down the real-world advantages here.
The absolute bottom line is this. You get all the stiffness and rigidity you need to protect those expensive parts and to keep the dunnage from warping after hundreds of uses, but you get it all without the heavy weight of a solid plastic part. And trust me, for the people or the robots that have to move these things around all day, that is a huge, huge deal.
But the benefits go way beyond just the weight. The real game changer, the thing that makes it even practical to make these huge parts, is the pressure used during the molding process. This is a really big deal. With your standard injection molding, you're basically blasting plastic into the mold with an insane amount of force. I mean, we are talking 3 to 4 tons of pressure per square inch. That requires these giant, expensive machines, and it can actually bake a lot of stress into the part, which often leads to warping down the road. Now get this, with structural foam, the pressure is down around just 1 ton per square inch. That massive reduction in pressure is the secret sauce that lets you create these enormous parts on smaller, more affordable machines. So, what does that lower pressure actually get you? Well, it means you can make much, much bigger parts. It gives you more freedom to design those thick, structural ribs you need for strength without worrying about ugly dents called sink marks. And because there's less stress locked into the part, you get way less warping and a much more stable, consistent shape. Oh, and you're using less plastic, which is a win for your wallet and for the environment.
All right, so now that we get the how and the why, let's get practical. How do you decide when to actually use structural foam compared to the other options? Let's walk through that decision.
Okay, let's just break it down side by side. If your number one concern is the upfront cost of the tool, thermoforming is usually your best bet.
If you just need a huge part, both thermoforming and structural foam are great candidates. But when you need consistent wall thickness and the ability to design in strong structural ribs, that's where structural foam is the undeniable winner over thermoforming. And while standard injection molding is king for fine details, it just can't touch the size and cost-effectiveness of structural foam for these massive applications.
Now look, it is a fantastic process, but it's not a magic bullet. Like any engineering choice, structural foam has trade-offs and some real constraints that you absolutely have to plan for if you want your project to be a success.
First up, the surface finish. That foaming process can create a kind of swirl pattern on the surface, so it's probably not your first choice if you need a perfect, glossy car hood kind of finish, what we call a Class A surface. Second, the basic rules of plastic design still matter. You have to think about wall thickness, where the plastic enters the mold, how it cools, all that stuff is still crucial. And finally, yeah, the pressure is lower, but physics is still physics. There are still physical limits to just how big a part you can pop out of any given machine.
So, with everything we've talked about, how do you actually make the final call? Well, we can actually boil all of this down into a really simple but really powerful decision-making framework. It all starts by asking yourself one simple question. What is the single most important, the one absolutely non-negotiable requirement for your project? Your answer to this one question is going to point you in exactly the right direction. And here's the roadmap. If your non-negotiable is the absolute rock-bottom tooling cost and getting it done as fast as possible, you should probably start your search with thermoforming. If it's all about holding incredibly tight tolerances and getting tiny, intricate details just right, then standard injection molding is your go-to. But if your absolute non-negotiable is that tough combination of large size, serious structural stiffness, and long-term durability, you should absolutely start with structural foam.
But here's the pro tip. The truly optimal solutions, they rarely rely on just one single process. The best designers think of the Dunnage as a complete system. They use the right process for the right part. So maybe you'd have a big structural foam base combined with smaller detailed clips made from standard injection molding.
And you know what? That system approach also tells a fantastic sustainability story. Right from the start, you're engineering lighter parts using less plastic. And when you think of it as an integrated system, you can design it for the end of its life, creating a recycling loop where old dunnage is brought back, ground up, and that material is fed right back into making new parts. It's a closed-loop system that can actually work in the real world.
So all of this brings us to one final thought. The next time you're staring down one of these big, tough design challenges, ask yourself this question. Are you designing just another component, or are you engineering a complete, integrated, and sustainable system? The answer to that could change everything.